Okay. Okay, hello everybody, and welcome to the Law Physics webinar cycle. Happy 2020, because this is the first webinar of the year. So this time we're gonna have a very nice talk, a webinar given by Ibrahim Safa. He's a PhD student candidate from the University of Wisconsin-Madison. And he have done this work that you can see in our WordPress page about on what is going to be the webinar. That is very impressive, the compilation of different observables and how it's related with dark matter. So Ibrahim, if you want, you can start your webinar whenever you want. And thank you for coming and to allow to talk here.
Awesome. Thank you very much. And I've always enjoyed watching these webinars, so I'm thrilled to be on the other side. Let's see if I can start sharing the screen here. Can everyone see the slides now?
Yes.
Okay, great. So what I want to talk to you about today is WIMP dark matter. I will summarize sort of the evidence we have for particle dark matter, and then discuss the constraints that we can get from neutrino observations that have only recently become possible, not only to make these observations, but to ask meaningful questions about the connection between dark matter and the standard model in a more broad way. And like you said, this is based on the work that my collaborators and I just put out recently. So we know that dark matter exists from gravitational effects overwhelmingly observed in several channels. I'll just very briefly describe a few. So this image I show here on the left, you see these blue arcs. That is caused by the bending of light coming from these distant galaxies in a cluster by an object that is between the observer and the cluster, but there's no visible matter between us. And when you try to fit for the distribution of matter that would give you such a distortion, you end up with this blue halo on the figure on the right. Of course, other evidence for dark matter comes from rotation curves. So this is where you measure the velocity of systems in a galaxy that as a function of the radius from the center. So if you have normal Keplerian physics, you expect that if you have the mass is concentrated near the center, that you will get something like the dashed line, and that the velocity will fall off as you go away from the massive center. But what we see from starlight and 21 centimeter observations, this data is for the Andromeda galaxy, but this has been observed for dozens of galaxies and galaxy clusters. And what you see is that the velocity distribution is pretty flat, which suggests that there is a more diffuse, massive halo that is first on larger scales than the visible matter, but also that it's driving the velocity of distant stars or objects in a cluster. And finally, there's the CMB measurements. So this is where we measure the radiation from the first scattering in the early universe, the last scattering in the early universe. And so what you see here is that the temperature fluctuations, so the power spectrum of the temperature fluctuations in the CMB, and these perturbations in the early universe are very important for structure formation. And so the amount of matter seeds these fluctuations, and we've measured these peaks and their amplitudes, their position and their amplitude, to less than 1% by now. And we know that there has to be a component of matter radiation that exceeds the baryonic matter that we know of. Now, there are explanations that invoke new modifications of gravity. But observations of merging halos, such as the bullet cluster that I show here, suggest otherwise. So the bullet cluster here is just an aftermath of a merger. And you see two images superimposed on each other. One is the X-ray imaging, which you see in red. And that shows you where most of the gas and dust is that is moving away after the merge. And then in blue, you see the lensing data. So this is just purely gravitational lensing, and that tells you where most of the gravitational potential is. And this cannot be well described by theories of modified gravity. You could think of it as if there's a halo of weakly interacting particles, they're going to be less affected by the friction of the merge, and so they will separate from the normal matter as we see here in extreme cases. Now, WIMPs are a simple explanation. As an extension of the standard model. You add a new particle with a new force that is connected to standard model particles in some way, and then you try to test for signatures of such a connection. What we typically do, what has historically been done, is you define some new dark force that connects your dark matter to your standard model particles, and you can check for such connections in several ways. One of which is through direct detection. This is where you're going from left to right here. So you're assuming that the dark matter scatters off of some protons, and then you constrain the dark matter nucleon cross-section as is done here. As you see, there's many experiments that are looking for this, but of course this assumes a coupling between dark matter and quarks. Now, another way you can do it is you can go bottom up, and so you can collide two standard model particles with enough energy to produce such a dark matter particle, and this has been done at colliders. So I show just one plot here for reference, but the complications here are that these are highly model dependent. So because you're usually looking for transverse missing momentum, what you do is you typically assume some momentum and you try to look for the missing momentum in a collision. And so this depends on not only the dark matter mass and the mediator mass, but on several couplings of the dark matter to the standard model. So what I will be focusing on in this talk is the indirect detection method, where you search for final products of the dark matter through decay or annihilation, and you typically look for it from extraterrestrial sources. This has been done with photons and charged particles in the past because, well, for simply reasons of practicality, it's always been easier to measure photons or charged particles than it is to measure neutrinos. But what I will hopefully convince you of today is that neutrinos are not only another measurement you can make, but an essential measurement you need to make in order to say something meaningful about dark matter. And so in this picture, if you take a step back and ask yourself, as if I make as few assumptions as I can I ask a meaningful question here? So any dark matter annihilation or decay into any standard model product will eventually lead to two stable final states, which are photons and neutrinos. So in any other branch, so if the dark matter interacts with gamma rays or quarks or charged leptons, you will always get photons and neutrinos, but the limits from neutrinos from photons will always be better, simply because they're easier to detect. But there's one invisible channel, which is the direct annihilation to neutrino pairs, and that is mostly invisible and can only be probed with neutrino searches. And if you assume that this branching ratio is 100%, you can not only say something about the dark matter annihilation to neutrinos, but you can constrain the total dark matter annihilation cross-section to any standard model product, because it is the weakest, most invisible final state. And so, there are models that predict that neutrinos are our only connection to the dark sector, and those are typically called neutrino portal models. I link one reference here, but you can look at the references within if you're interested. And these models typically invoke some mixing between a heavy neutrino and the active neutrinos, and then the heavy neutrino is the one that talks to the dark sector, and in that case, you won't see any other signatures with the exception of the neutrino sector. So to make this, to ask this question, you need to detect the flux of neutrinos coming from dark matter annihilation. And there are two contributions to that. First is the galactic contribution. So these are neutrinos arriving from the galactic center mainly, where there's a high concentration of dark matter. And that flux depends first on the thermally averaged annihilation cross-section. So we do it for three cases. The first case is where this cross-section is velocity independent, and then we expand in powers of v and look at the velocity dependence. The neutrino production spectrum from annihilation is simply a delta function in this case. And finally, the J factor, as it's referred to, is just the integral of the dark matter density along the line of sight. And for this work, we used a generalized NFW profile in which there are three free parameters that were floated and fit for using rotation curve data of our own galaxy. So the limits I will show later on use the best fit parameters from this work, but we've also included the uncertainties, and I can show you those as well. The other contribution is a diffused contribution of neutrinos. So you expect that every other halo in the universe will also produce neutrinos. And so now this extragalactic flux coming at you from all directions will depend not only on the single halo profile, but also on the distribution of halos in the universe. And so this flux depends on the Hubble parameter. The production spectrum is still a delta function, but the energies are redshifted. So we rewrite it as a delta function in redshift. And then finally, the J factor that I used before is now not only integrating over a single halo, like I said, but it's also integrating over the distribution of halos as a function of mass and redshift. And of course, there are uncertainties. This is the biggest uncertainty for this type of calculation, uncertainty on the distribution of halos. And there are several models that use both simulations and first principles to derive these halo profiles. And so I show 4 of them here. We use Watson et al., which is the recent one, we also use all 3 other ones to characterize our uncertainties. And this gives you a factor of 5 or so, up to an order of magnitude of uncertainty on your cross section. So we take Watson et al. And use the most conservative assumption of a minimum halo mass, because the smaller the mass of the halo, the more concentrated it will be, and the more concentrated it is, the more annihilations you will get. And so we assume just a 10 to the minus 3 solar mass as the minimum halo mass, and we vary it up to 10 to the minus 9. Now that we've calculated the flux of neutrinos, you have to first detect the neutrinos to see how to see if you can see this feature. And what I show here is a plot of the flux of neutrinos arriving at Earth from extraterrestrial sources as a function of energy. And at the lowest energies, you have the cosmic neutrino background. This is analogous to the cosmic microwave background, where you see the surface of the last neutrino scattering. Of course, it's at too low energies to be detected so far, but there are efforts to do that. As far as solar neutrinos goes, we have detected a significant fraction of that flux. There's a diffuse supernova background that comes from the contribution of all supernovae that have happened over the history of the universe. And then at the higher energies, you have atmospheric neutrinos caused by collisions of cosmic rays with the atmosphere, and then astrophysical neutrinos, which are hypothesized to be caused by jets that are accelerating protons hitting a target and producing TeV to PeV neutrinos. And then at the highest energies, there's the undetected cosmogenic flux, which for the purposes of this talk, we use upper limits from these fluxes. And this is just caused by collisions of ultra high energy cosmic rays with the CMB. And that gives you a flux of guaranteed flux of 10 to the 18 and EV neutrinos. Now, this would not have been possible only 20 years ago because most of these fluxes were either measured poorly or not measured at all. And just in the last couple of decades, we've seen a major advancement in the experimental side of neutrino physics, where you have massive detectors that are increasing not only in size, but also in resolution. And so we have now a coverage of a wide range of masses, which gives you a wide range of neutrino flux detections. So I will talk about a few of these, but we have put all of the relevant experiments in a table in the paper. And as you can see here, there are many channels that you can look for, and that depends on the detector technology, whether it's Cherenkov or a scintillator or a TPC. And in most of these cases, you get directional information as well, and you can use that to better constrain your galactic flux. And as you can see, we're covering an energy range here of 2 MeV to more than an EeV, as I'll show you a bit later on. I will only talk about a couple of these experiments in depth, one of which is SuperKamiokande, and that is a 50 kiloton water Cherenkov detector in the Kamioka mine in Japan. It's been operational for quite some time now, and it has measured a atmospheric neutrino flux in the GeV to 10 TeV range. You can also measure the diffuse supernova neutrino background, although it has not been measured yet. There's an upper limit on extraterrestrial electron neutrinos that we also use here. And so there are several ways you can look for dark matter signatures here. You can either look in the direction of the galactic center. You can look for an excess above the diffuse flux, the isotropic flux, let's say, or you can look for an excess above the DSNB. Now, the next experiment I'll talk about is IceCube. So if you look here, this is a human on a boat in SuperKamiokande, and the scale roughly of this human to SuperK is what SuperK is to IceCube. And IceCube is a gigaton detector in the South Pole, about over 5,000 photomultiplier tubes instrumented in a kilometer cube of ice. IceCube, since its completion in the mid-2000s, has measured a diffuse astrophysical neutrino flux in the TeV to 10 PeV range, and has measured atmospheric neutrinos in the GeV to 200 TeV range, and it has set limits on the EeV flux of neutrinos, the highest energies. So we'll use all of these to to constrain the dark matter. And then, of course, there are many, many more experiments that I just briefly showed earlier. And so there's Borexino, which is a liquid scintillator experiment in Italy that measures solar neutrinos. There's also CAMLAND, which is actually a reactor experiment, but it has set limits on extraterrestrial neutrinos. I think it's electron antineutrinos at the MeV scale. There's Antares, which despite being about 1% the size of IceCube, is in the right hemisphere to look at the galactic center, because the Earth is in the way, so it blocks most of the muon background, and then you get a very clean signature of neutrinos from the galactic center. And then there's Auger, which is a cosmic ray experiment, but it is also sensitive to the EEV neutrino flux, and we use their limits to constrain the dark matter flux as well. In the future, there will be experiments such as DUNE, CTA, TAMBO, and GRAND, which will all be sensitive to these neutrino fluxes all the way from the GeV up to the EeV scale. And we'll show projections here in a second. So the expected neutrino flux, this is from the extragalactic contribution, now showing data from both SuperK and IceCube. And this goes from all the way from 100 MeV to a PeV. So on the left, you have a plot of the nu mu atmospheric flux, and for some chosen dark matter mass, and the cross section that we find is ruled out at 90%. You see the flux is superimposed on top of the measurements here. And we also do the same for, of course, electron neutrinos. And then on the bottom right, you see the all flavor isotropic astrophysical flux, which we can also use to constrain dark matter signals at the highest energies. Now, this is what we find. Impressively, these limits are uninterrupted from about 10 MeV all the way to a ZeV. So that's, you have about 15 orders of magnitude of constraints on dark matter annihilation, starting from Borexino to lowest energies all the way up to Anita at the highest energies, which I will show in a second. Another thing to note is that some experiments are finally reaching the thermal relic abundance, which historically has not been associated with a neutrino channel because it's notoriously difficult to do these measurements. But this is very hopeful for the future, and that HyperK will definitely be able to probe this lower region. So if we zoom in a little bit, you see Borexino at the lowest energies, and then CAMLAND and SuperK takes over pretty quickly here as it becomes sensitive. Now, these are taken from several different event selections. We're not part of the SuperK collaboration, so we couldn't use event by event information for all of these limits. Every limit that has a heart on it is a limit that we've set. Other limits are either referenced or are assumed to be done by the collaboration itself. This one here is from SuperK4 data, the most recent data that was made public in the last year. And then this here is using the SuperK atmospheric flux at the higher energies. And then the gray band is Olivares et al., where they constrain the annihilation using the diffuse supernova neutrino background. We show projections, of course, for DUNE and HyperK. These are conservative projections because we do not assume any directional information, and directional information can be very important, actually. So we think these limits can only be made better by a dedicated sensitivity analysis from these experiments. If we go to the high mass region, of course, you have Antares over here. Which, like I said, even though it's smaller than IceCube, it is in the right hemisphere to be making this measurement. And then in the future, KM3net will be able to probe even closer to the thermal relic abundance. At the higher energies, IceCube takes over, where these limits here are set from the diffuse astrophysical flux And then the EHE limit here is the limit we have set on the EEV neutrino flux. And then you see projections from, for example, GRAND, which is a radio experiment proposed to be built in China that will be composed of 200,000 radio antennas that will cover 200,000 square kilometers to measure the cosmogenic neutrino flux. And then the limits from Auger, Tambo, and Anita are shown here as well. Now, of course, we didn't just stop there. We looked at the velocity-dependent annihilation cross-section. These limits are, of course, less constraining because fast dark matter tends to not want to clump and annihilate as much. And so these limits we show just for model comparisons in case you have models where these velocity-dependent cross-sections dominate. And so we do this for the case of P-wave annihilation, where it depends on the velocity squared, and for D-wave annihilation, where it depends on the velocity to the fourth power. And of course, it's mostly a scaling of these limits from the velocity-independent case. Okay, I will just summarize here that the nature of dark matter and its relation to the standard model are still open questions, but we know that there is new physics in the neutrino sector, and we've known that since at least the mid-90s. And so it is not only interesting, but essential to ask, can the new physics be derived from connections to dark matter? And it is also an essential complement to searches with photons and charged leptons, because those limits could be evaded with certain models, but the neutrino bounds are essentially the upper limit that you get on dark matter connections to the standard model. Finally, there have been some major experimental advances in neutrino detection that have made this question possible to ask and allowed us to probe a mass range spanning 15 orders of magnitude. This was thought to be, of course, unlikely, and even when I talk to people at conferences, they simply say that historically it's always been dark matter has always been searched for with photons simply because it's easier. Well, I hope now we can see that it is also relatively simple to look to ask these questions through the neutrino channel, and these advances have allowed us to do that. And then the next generation experiments will finally reach the thermal relic region, which will start constraining once and for all WIMP dark matter models. So stay tuned for that, and thank you for listening.
Okay, thank you, Ibrahim. So first of all, thank you, Ibrahim, for the talk. It was very interesting. But for older listener, you can start to write question for him. We are gonna read it later. And for the people also that is interested about what is low physics, you can go to our WordPress page to subscribe to our YouTube channel and follow us in the Facebook and all the pages that we have. So to not get lost about when, how, where we are gonna have the next webinar. So let's start with some questions, especially for the people here in the Zoom session. I don't know if one of you guys has a question for Ibrahim.
I have a question.
Okay, Nicolas.
Can you guys see me? Yeah. So thanks first for the super nice talk. So I have a question about your limits. When you show, for instance, in slide 23 or 24, yes, exactly. Why the limits are so like edgy? Why are they not like smoother like that?
Yeah, so these are, so again, we did these from public data, and this is usually binned upper limits or binned data. Of course, these limits could be made smoother or better by the collaboration itself, but you need event by event information for some of these, like the SuperK purple here. if the collaboration does this analysis, it will be similar to this green curve. But since they only provide us with binned atmospheric data, this is the best we can do with the public information. As you can see, the limits that are set by collaborations are usually tend to be smoother. It's also a function of how we set our limit. So we use here a truncated Gaussian likelihood, and we set the limit at 90%. So this is a very it's a very peaked sort of signal.
Okay, I see.
Yeah.
And just out of curiosity, why do you have some hearts?
The hearts are the ones we made. So any limit with a heart is one that we have computed. Ones without a heart are ones that others have computed.
I see. Thanks.
You put more feelings in those analyses, in the one with the hearts.
Yes.
So we have a question from YouTube. I don't know, Nicolas, if you have more questions.
No, for now it's okay. Thanks.
Okay. I mean, later you can ask more if you want. But yeah, now we have a question from YouTube, the Andre Lesa. He's asking, how is the background neutrino flux handled when the computing the limits? Is the normalization shape fixed or fitted to the data?
So the background depends on the experiment. For example, in the case of Borexino, at the lowest energies, we simply use an upper limit. So there is no technically there's no background there. For the SuperK limits that use atmospheric neutrinos, we assume so we take the isotropic atmospheric flux because we don't have any directional information again, and then we compute the directional dark matter neutrino flux from dark matter and require that the directional flux is higher than the isotropic atmospheric background, which is a conservative approach, but one that avoids issues like having to account for the direction of these events, which we don't have. So the background depends on each experiment. For the most part, it's the atmospheric spectrum or the astrophysical spectrum. In the case of Antares, this was a collaboration limit, so they handled their backgrounds, I think, by looking at atmospheric events in the bin of the galactic center. But we just assume the null hypothesis is simply the atmospheric isotropic flux, and then increase the dark matter flux such that it exceeds the measured neutrinos. I hope that answered the question.
Yeah, I mean, Andrea can. No, we have other questions, but yeah, Andrea, he can comment in the YouTube chat if he wants more details, something like that. No, he said great, thanks. So anyway, we have more questions in YouTube. Let me just copy there so you can see it, but I'm gonna say it to the public to. Okay. Okay. Ardechin Pakfar, he's asking, consider the 3000 K years of atomic recombination before the CMB, how much the number of neutrinos be multiplied to as considered as serious candidate for dark matter? And he has another question that is, I'm wondering if we can consider them as a slash of neutrinos if we consider their gradient instead of the hot individual behavior, we can see the impact them as dark matter. So he is asking if neutrinos can be the dark matter candidate in general.
Right. So like I said before, of course there are many channels. What we're simply asking is, if there's any connection between the dark sector and the standard model, the most invisible, the hardest, the weakest final state will be the neutrino channel. And so just assuming that the neutrinos are the final product gives us the most conservative upper limit on dark matter annihilation in general. So this is not really just constraining the dark matter annihilation to neutrinos. This is assuming that, probing the weakest final state will give us the most conservative upper limit on dark matter connections to the standard model in general.
Okay, so let's see if and I don't know if somebody else has a question, because I'm gonna say,
let me ask a couple questions.
Because then I start and I don't finish.
Yeah, because then you can start and then you go on and on. So yeah, so mine as usual regarding dark matter are basic. So the thermal relic abundance curve, right? So that is the value of the thermally average cross section that would be required for the dark matter to give the observed relic abundance, assuming it's thermal.
Yes, that's true.
And that is assuming that the only cross section there making it thermal is that to neutrinos.
I think so, yeah.
So that's the case, right? So you're assuming so that curve is valid only if, I mean, you're saying, okay, of course, that the neutrinos are that the dark matter is annihilating only into neutrinos, and then you're saying that also, you know, okay, of course, in their interaction they will interact only with neutrinos.
I think that the relic abundance is fairly fixed, regardless of the. I mean, I'm sorry, the cross section that would produce the relic abundance is fairly fixed. This is assuming a single channel, but you would get the same cross section for any single channel, I think.
Okay.
So of course, if you have more channels, you're going to have to scale this cross section by the branching ratio.
Yes.
But if you just assume that the dark matter, let's say, annihilates only to photons, you'll get the same thermally average cross section.
Okay. Okay. Great. Okay. Think and one other thing. And did you say what that unitarity bound curve was? I missed that.
Right. So the unitarity bound is a theoretical bound that is derived from the fact that you want some of your scattering probabilities to be 1. So this is a statement on the S matrix being unitary.
Right.
And so in that case, you would have to be below this bound. But since this work was aiming at collecting all of the neutrino data and deriving limits in all the energy or the mass ranges, we made no assumption on the unitarity, and so that would, it would have to depend on the model which you're building, and so you would compare it to these limits. But yeah, I don't know if that makes sense.
Yeah. No, fantastic. Yeah, that was what I thought, but I wasn't sure. And okay, the last question so that Roberto can take over. So okay, this is more of a model dependent view, right? So for instance, if the dark matter were, say, KV neutrinos, which okay are having a hard time with the, what's it called, the Nustar bounds, right? But okay, in principle, if you have these KV neutrinos, they could annihilate into lighter neutrinos, but they will also decay into photons and neutrinos, right?
Right.
So in principle, you will also get a flux from their decay into neutrinos.
That's true, yes.
So how would, in this kind of scenario that you have the dark matter also decaying into neutrinos and something else, or like into 3 neutrinos, right, or something, how would these bounds be modified?
So the case that the sterile neutrinos at the keV scale are the dark matter, they run into problems with cosmology. So you would have to assume that they're non-thermal. So it would have to be some sort of dynamic production of these keV steriles.
Right. That's because of the Big Bang nucleosynthesis
exactly,
issues? Yeah. Okay.
Yeah.
Okay. Great.
And so these are best searched for with X-ray lines, which is what the experiments such as the sounding rocket Micro X are doing, where they're launching calorimeters into space and trying to measure these KeV X-ray lines, which are notoriously very difficult to detect. And so the best way to look for these sort of signatures would be in the X-ray regime. Mostly because there are no natural neutrino fluxes at that scale that are detectable. So it's hard enough to see atmospheric neutrinos, which there are many impinging upon us. But at the KeV energies, the cross section is low, and we don't know of any steady or directional flux of extraterrestrial neutrinos that we can look for from there. As far as how it would modify the limits I show here, I'm not sure. I'm not entirely sure how that would work.
Okay. Okay. Well, thank you very much.
Thank you.
Okay, Ibrahim, I have a question. In the sense of, okay, all of you made the analysis with the flux of neutrinos coming from annihilation of dark matter, but usually there are same scenarios with annihilation of dark matter going to intermediate particles. Let's say annihilation through BB bar,
right,
pair of quarks. Then you get a much softer neutrino flux. Even
right.
And also there are these other issues. For instance, for heavy dark matter, that is the electroweak prestralum or electroweak production. How they could impact these limits, because in any case, it's going to be model dependent.
Of course.
I mean, generically model dependent. Even the
right. Well, yeah. So the case we make here is that if it annihilates to BB bar, any quark pairs, the limits you get from photons will always be stronger, right? Because those are unavoidable photons. But if you assume that dark matter only annihilates to neutrinos, then you can evade the bounds from photons. And then, you get to the point above a few hundred GeV, like you said, where you have electroweak Brem of W bosons, which will also give you photons, right? Now, the limits we show here are better than the limits set by photons for the same channel, except for CTA, which does not yet exist, but is under construction right now. So you see the silver line. So the silver line is derived from the gamma rays you would get from neutrinos produced at these energies that would then Brem and give you these gamma rays. So CTA will finally be able to say something better than the direct neutrino searches, but in the wide energy range here, or the mass range, you're mostly better off looking for direct neutrino signatures. And so like I said, branching ratios to any other channel have been constrained heavily by Fermilat, by Hess and Hawk, and so these experiments have much better sensitivity to the other channels, and so you can kind of, if you're trying to combine all of these things together in a single picture, you would say, all the other channels are typically ruled out in the region of interest, with the exception of the neutrino channel. And so that can provide you, if you try to cook up some model that would only give you, the dark sector would only talk to neutrinos, then this is the final, let's say the final frontier for WIMP dark matter before you can finally put it to bed, basically. Yeah.
Okay. Yeah. In fact, that for me was impressive. Indeed, this plot that you're showing the how many order of magnitude there is data,
right,
and could be analyzing the
exactly, and how flat it is, right? Because these fluxes are dropping a lot from the lower energies to the higher energies, but it's an effect of both how the cross section of neutrinos rises so quickly, and the fact that these detectors are becoming bigger and bigger as you go up higher in energy. So these effects kind of balance themselves out, and you get kind of a flat constraint over these many orders of magnitude.
Yeah, but in the case, maybe it was Nicolas was asking similar. In the case of decaying dark matter, this limit could be easily scalable, no? I mean, for a generic decaying dark matter that decaying to two pairs of neutrinos. just, I mean, the most simple scenario. I don't know.
Right. They could be just naively rescaled, but we can also just do a similar thing to decaying dark matter, where we just look at decaying signatures. So these plots would be, somewhat flipped, because the dark matter decay depends on the lifetime, and it's 1/m, not 1/m², I think. So
Yeah.
they'll have slightly different slopes, and then the limits would go up, and you'd set lower limits on the lifetime. But yes, in principle, you can sort of squint and try to see what the decay limit would be from these.
Yeah.
So one could do a similar thing with decay.
Yeah, it could be interesting because of sometimes when you compare decaying dark matter scenarios in photons, for instance, gamma rays from the galactic center, they are much worse constraining than the gamma rays coming from the halo, because, okay, in annihilating dark matter, you have an enhancement because of the density squared of dark matter, but yeah.
Exactly.
The other is more smooth. Maybe for the neutrino could be also a scenario that could give a surprise. I don't know.
Right. Exactly. I mean, we were kind of halfway into doing the decay case, but we realized that the work is already big enough that we would put it out and then kind of separate the ideas a little bit. So
yeah,
I would
good.
Yeah, stay tuned for the decay case.
Okay, so if anybody has a question, do it now. People in YouTube, please write your last question if you have. Otherwise, we can close it for today. First of all, of course, again to say to Ibrahim that it's very nice that the talk that he gave, and congratulations. And for the rest of the people that is interested, as said, on Law Physics webinar, we have all the previous webinars in this YouTube channel. You can check, and maybe if you are interested in a topic, you can contact the speaker and maybe to see what you can collaborate with them in the future or something like that. So for the rest of us, thank Ibrahim. See you in the next time for the more webinars, maybe in 2 weeks more. And that's all for today.
Thank you so much.
Okay. See you,
Appreciate
everybody.
Right. Bye-bye.